Welcome to the Professor's DuBois channel. This is Professor Corey, and this is a little mini lecture based on material from Chapter 11. It's our third lecture in the series from Chapter 11, and we begin it with the properties of liquids. And we've got a list of the properties here with some definitions, and some of these definitions are a little bit confusing, so we'll go into them in a little bit more detail. So what we're really concerned with is how does intermolecular force strength affect the properties of these liquids? And this is kind of a summary of these. And it's tempting to try to memorize these relationships, and I strongly advise against it. Rather than memorizing, I'd rather you could conceptualize, like what's going on with the material, how do the forces affect the material, and really we're looking at molecular shape, and if it's polar, we'll have the dipole forces, they're strong. Look for hydrogen bonding, look for nonpolar molecules, they have weak intermolecular forces, and really try to understand what's going on based on the strength of the intermolecular forces rather than just trying to memorize these facts. So we've got this definition of a normal boiling point, but really what makes it confusing is there's the word vapor pressure in there. So, what is vapor pressure? So vapor pressure, the liquid reaches atmospheric pressure. So let's talk about vapor pressure. This is a visual that shows how we can have a vapor. So we've got initially we have a volatile liquid in a container, and we've got mercury in this little tube. It's glass. It's a glass tube, and it's shaped in like a U shape. And so we have a volatile liquid, and that just means that it'll evaporate fairly easily. And over time, the gas, we can see that on the right, the brown color, the gas will occupy that entire container up to where we have the valve closed, and it's actually pushing down on that mercury. And you can see that we have a distance that the mercury has traveled up the tube, and we can measure that in millimeters, and that's where we get our millimeters mercury measurement. So this is vapor pressure. Vapor pressure is the pressure of the vapor above the liquid. And we can look at this, in a simple drawing, and what we're trying to show here is that we've got water at 20 degrees C on the box on the left, and there are molecules of water that have enough energy to escape into the vapor phase. So when we have vapor phase, it's exerting a pressure on this container, and we've got a measurement device on the top there that says, okay, it's 0.03 atmospheres. Now that's a made-up number, but we're going to go with it for this. So what we're saying is that water at 20 degrees C has a vapor pressure of 0.03 atmospheres. Now, bromine, Br2, nonpolar molecule, at the same temperature would have a higher vapor pressure because the intermolecular forces are not as strong. All we have with the bromine are the dispersion forces. So there's going to be a lot more molecules of bromine that can escape into the vapor phase. So we have the vapor pressure here at 0.30 atmospheres, and I'm not certain that these are accurate, but we're just trying to show that water with its polar molecule, it has hydrogen bonding, would have a much lower vapor pressure than something that was nonpolar. And an interesting thing about vapor pressure is it's a set value at a given temperature. So it doesn't matter how full that box is with water or bromine, we're going to have that same vapor pressure as long as there's liquid present. So there could be 5 mils of liquid, and there'd be a pressure of 0.03 for water and 0.3 for bromine, or it could be full nearly to the top, just a little tiny airspace, and the vapor pressure would still be the same. And that's an interesting thing to think about. This is a chart that's showing vapor pressure at different temperatures, and you can see the trend here is that when we increase temperature, we increase vapor pressure. And this makes sense because what's happening to create vapor pressure is the liquid molecules are escaping the liquid phase and getting into the gas phase. So if we increase the temperature, that's going to allow more molecules to escape and get into the gas phase. The next thing we're going to talk about is the enthalpy of vaporization. And we also call this the heat of vaporization, and we see this delta H value. Sometimes I call it the energy of vaporization. And the delta H, the delta, that little triangle symbol, just means the final minus the initial. And this is the amount of energy it takes to vaporize a liquid to form a gas. So in this example, we have 1 mole of liquid water going to 1 mole of gas, and we have a delta H value of 40.7 kilojoules. So that's the amount of energy it would take to put 1 mole of water, liquid water, into the gas phase. And realize this is a factor. So we've got 1 mole at 40.7 kilojoules. So if we had 2 moles, that would be double that, or 81.4 kilojoules. We can set this up and do dimensional analysis and use it like a factor. So we're looking at the trends in the energy or enthalpy of vaporization. And if we look at the, let's say, water, we're familiar with water. Down near the bottom, it's got a value pretty high, 40.7 kilojoules per mole, compared to, say, helium. Now, helium's very, very low. So helium it takes very little energy to vaporize helium, and at room temperature, helium is a gas, as is argon and methane and ethane. So we've got methanol that has a value of 35.4 kilojoules per mole, a little less than water. Now, the relationship here is that the stronger the intermolecular forces are, the higher the energy or enthalpy of vaporization. So with water and methanol, they both have hydrogen bonding, but remember that water has 2 hydrogens that can hydrogen bond. So those forces are a little bit stronger than those in methanol. Same slide, vapor pressure and temperature. And I want to just call out one thing here, that we have this thing called the normal boiling point. And the normal is kind of like a room pressure. So if it's in millimeters mercury, it's 760. So it's right here. That's 760. If it's in atmospheres, it'd be 1 atmosphere. Now, a lot of times there'll be like a dotted line in these graphs going across. So if I made a dotted line, I stayed right at 760, doing the best I can. And when I get to the line here, the carbon disulfide line, if I drop straight down, I can get the temperature, and that's going to be 45 degrees C. That's the normal boiling point for carbon disulfide, is 45 degrees C. So back to that definition, when the vapor pressure reaches the atmospheric pressure, we boil. So regular atmospheric pressure, 760 millimeters mercury, and at 45 degrees Celsius, we're there for the carbon disulfide. Methanol would be right about 65 degrees C, and ethanol almost, between 75 and 80 degrees C. So we can see that we do have a trend. Vapor pressure increases with temperature, but also realize when we have these graphs, we can get the boiling point. We just have to have the normal pressure, which is going to be 760 millimeters mercury or 1 atmosphere of pressure. So look for that on the y-axis, and you can make a line over to the curve, and you can drop down and get the temperature, which is going to be the boiling point. So just a quick summary. Vapor pressure increases with increasing temperature. Strong intermolecular forces lead to low vapor pressure. Vapor pressure doesn't depend on surface area, and that's going back when I was talking about how we can have different amounts of liquid in the container and we'll have the same vapor pressure. Well, we could change the size of the container. It could be a long, skinny tube that had the liquid in it, and as long as there's liquid present, the pressure of the vapor above is going to be a set value for a given temperature. The next thing we're up against is this Clausius-Clapeyron equation. And what this is a relationship between the pressure, temperature, and the enthalpy of vaporization. So we've got the relationship on the very top box, and then we have this straight line version, which is simply we rearranged the equation and brought out the 1 over t. So you can see that we've got the formula of a line here. So we've got the log of p, natural log, is if we plot this on the y-axis and we plotted 1 over t on the x-axis, the slope would be the negative delta H vaporization over R. And this is the ideal gas law constant, but the units are in joule per Kelvin mole. So it might look a little funny to you, but this is correct in these units. Now the 2-point version is a pretty common one on tests because this one kind of requires you to make a graph, although I suppose we could give you the graph and you could determine the slope to figure out the enthalpy of vaporization. Be a better lab, it'd be better to do in lab probably. But this 2-point version, we can give you, 2 temperatures and 2 pressures. You can solve for the enthalpy of vaporization. We could solve for a pressure if we had the enthalpy of vaporization and the temperatures, or we could solve for a temperature. Now, this equation can be a real monster to solve, and a couple things I just want to point out where people usually make mistakes. And one thing is it's that negative sign by the delta H of vaporization. If you forget that, and I often do this, your answer will be wrong. So remember, like I'll use a highlighter and I'll just highlight that negative sign so I don't forget. And the other thing is this 1 over temperature, which the temperature has to be in Kelvin because of the units on the R value. Don't round those numbers when you divide. So rounding those really affects the result quite a bit. So this is just showing how we could use, if we had some temperature and pressure data, we could make a graph, and the slope would be negative delta H over R. We'd have to solve for delta H. Now, when we're doing this equation, like the 2-point equation, one thing that's just worth mentioning is there's a couple log rules here. And if we have the log of P2 over P1, the way the equation's written, we can rewrite that as the natural log of P2 minus the natural log of P1. And you might find that useful when you're doing these problems. And the other thing is when you say we're trying to solve for the P2, a second pressure, and we finally get down to the end, we've got the natural log of P2 equals 0.69315. The way we get P2 is we take the inverse log of the 0.69315, and that's e to the x. Usually on your calculator, it's going to be the second function with the log button. So be aware of that. These will take a little bit of practice, and you'll be able to solve them. It's an exercise in patience. So the last slide we have here is we have a question. This question's in your summary packet, and I actually made a separate video, and I kind of walked through the calculation. So give this a try. If you're having some trouble, check out that other video where I walk through this calculation slowly. So hope this is helpful. If you like it, please give it a thumbs up. I appreciate your time. And stay tuned for more mini lectures with the Professor's DuBois channel.